Hello friends. So today we are going to solve the questions from the year 1993, and the total questions are 2. From the year 1994, number of questions is 1. From the year 1995, questions are 2, and from the year 1996, the number of questions are 3. So in totality, we are going to solve 8 questions. And first question, which was asked in the year 1993, and it states that a circular ring of radius r with uniform positive charge density lambda per unit length is located in YZ plane with its center at origin O. A particle of mass m and positive charge q is projected from a point P whose coordinates are given as r square root of 3, 0, 0 on the positive x-axis directly towards O with an initial speed v. Find the smallest non-zero value of the speed v such that the particle does not return to P. So in this case, we are given a circular ring which is having a radius r. So we can just draw an approximate figure for that, and suppose this is our thin ring and whose radius is our r, and it is in YZ plane. This is our y-axis, z-axis, and this is our x-axis, and we are said that a particle P, so let us mark a point P. Suppose this is point P and its coordinate is given as r square root of 3, 0, 0, and it is at a distance of x from the origin. So this is origin O and it's a distance of x from the origin, and we are also given the radius, that radius is our r, and we need to find out, and the particle is okay, and there is a charge at P which is having charge q and mass m, and it is projected with the velocity v towards the origin, and it is given that the ring has a positive charge density of lambda per unit length. Okay, so both are positive. The charge that is being projected is also a positive, and the charge density of this ring is also given as positive. So by default, there will be a force of repulsion between the charge that is q as well as the ring, and we need to find out the speed v such that the particle does not return to point P, that we are required to find out. And in this case, we are going to use, you can say, conservation of energy, and then we can also use the potential at point P and potential at the center of the ring. Okay, so we can say, based on this, we are going to find out the change in potential energy. It means potential at O, that is the origin, and potential at P. So that difference is going to give us a change in the potential energy. So we start with our potential at center O, And for that, let us first of all find out the total charge in the ring, because we are given that the charge density is equal to lambda. Therefore, we can say the total charge of the ring, let us suppose that is given as q, then this q will be equal to the circumference, that is 2 pi r, and multiply by lambda. So this is the total charge on the ring. And therefore, based on this, we can find out the potential at the center O. So you can say potential at the center of the ring let us suppose that is given as V naught, and that V naught will be equal to 1 upon 4 pi epsilon naught, the value of charge, that is our Q, and divided by R. And if we substitute value of Q, we can write that our V naught will be equal to 1 upon 4 pi epsilon naught, and this comes as 2 pi r multiplied by lambda and divided by r. And this pi and pi, r and r cancels out, and 4 goes by 2. So we get our V naught will be equal to lambda upon 2 epsilon naught. So this is the potential at the center O. Similarly, we can find out the potential at point P because of the ring. Okay. So let us draw this figure again. So now the ring I am going to represent only by a circle, and we have a point P that is somewhere here, and for the sake of convenience we assume that this distance is our x and r is the radius, and we have a positive charge all along the ring. And that is given as q. So therefore, this length will be equal to our r square plus x square and its square root, and the coordinate of P is given to us, and the coordinate of P are our square root of 3r0, 0. So this is nothing but our value of our x, coordinate of x, that we can substitute. So we can say the potential at point P at point P, let us call that as Vp. So Vp will be equal to 1 upon 4 pi epsilon naught q, and the distance between them is our r square plus x square square root, and q we already know, and we also know value of x, so we substitute it, we get 1 upon 4 pi epsilon naught. Q is our 2 pi r multiplied by lambda, and we get this as our r square plus, we have it as r square root of 3 and its whole square and square root. So once again, our pi, this goes by 2, so we can say our Vp will be equal to 1 upon, let us suppose this is lambda, or we can say r lambda divided by 2 epsilon naught, and we can solve the denominator, that will be equal to r square plus 3r square, which comes as 4r square, and 4r square square root will be equal to 2r. And once again, here r and r cancels out, therefore we get our potential at P will be equal to lambda upon 4 epsilon naught. So we got the potential at the center O as well as point P. Now from here we can find out the change in the potential energy. Okay, because charge Q is going to travel from P to O. Therefore we can say that change in potential energy, let us call this delta of U, will be equal to charge, and we have this as V0 minus Vp. We substitute the values, we get this as delta of U is equal to Q times V0 is our lambda by 2 epsilon naught minus lambda upon 4 epsilon naught. This will be equal to, this comes LCM will be over 4, and this comes as 2 minus 1, that is 1 upon 4. So we get from here, we get Q lambda 4 epsilon naught. This is the change in the potential energy. Now we can find out the change in the kinetic energy. Change in kinetic energy, let us call that as delta of K, will be equal to 0 minus half m v square, which comes as minus half m v square. Now we can simply use the conservation of energy. You can say conservation of energy This gives us that our delta of U is equal to delta of U plus delta of K is equal to 0. We substituted delta of U was our Q lambda upon 4 epsilon naught. This comes as minus half m v square is equal to 0. We substitute, we can just now it is sorted out, and we are interested in our velocity. So this comes as half m v square is equal to Q lambda 4 epsilon naught. This 4 goes by 2, and we can say that our velocity V will be equal to, this comes as Q lambda, and this will be 2 m epsilon naught and its square root. So this is the our velocity, that is the smallest speed that is required. Next question, and it states that it was asked in the year 1993, and it states that two parallel plate capacitor A and B have the same separation D, that is 8.85 into 10 to the power minus 4 meter between the plates. The plate areas of A and B are 0.04 meter square and 0.02 meter square respectively. a slab of dielectric constant, that is relative permittivity K is equal to 9, has a dimension such that it exactly fills the space between the plates of capacitor B. So based on this, we have 3 questions. In the A part, it states that the dielectric slab is placed inside A as shown in 1. A is then charged to a potential difference of 110 volt. Calculate the capacitance of A and the energy stored in it. In part B, it states that the battery is disconnected and then the dielectric slab is removed from A. Find the work done by the external agency in removing the slab from A. And in the C part, it states that the same dielectric slab is now placed inside B, filling it completely. The two capacitors A and B are then connected as shown in the figure. Calculate the energy stored in the system. So this ABC, you can say, is in the first part it states that we have capacitor A and there is a dielectric inserted in it and the supply voltage is 110. We need to find out the capacitance of A and the energy stored in it. Okay. And in the B part, which is also with respect to figure 1, it states that battery is disconnected and then the dielectric slab is removed. So this figure 1 will be the second part, we can say will be something like this. So this is our dielectric and this is A, and now there is no battery source. Okay, it has been removed. And along with this, you can say the dielectric slab is also removed. Okay, so there are major 2 differences between figure 1, that is called is 1A, and this figure 1 is 1B. So the 2 major difference, first is there is no supply and that dielectric is also removed from figure within the capacitor A. So this is the our first. Okay. Okay. So for the part A, so from the part A, we can clearly see from the figure itself that the net capacitance of capacitor A will be equal to combination of 2 capacitors. One will be our consisting of CK, that is when the dielectric is inserted, and other one is our normal, and both of them are in parallel. Okay. Therefore, we can say that capacitor A is a combination of 2 capacitors. And first capacitor, let us call it as CK, and that is our having a dielectric, and second one is our C0, that is our without dielectric, and they are in parallel. Therefore, we can write our capacitance CA will be equal to our CK plus C0. So we come this as C epsilon naught A upon D plus this comes epsilon naught A upon D. So we can write this as K plus 1, and here we have epsilon naught A upon D. And area as well as this separation is given to us, and we also know the value of epsilon naught. So we substitute it, and we get that our CA will be equal to, this value of K is also given to us, that is our 9 plus 1. Our epsilon naught is our 8.85 into 10 raised to power minus 12. Area is given to us 0.02, and the distance between them is also given, that is 8.85 into 10 raised to power minus 4. So we get our CA will be equal to 2 into 10 raised to power, this comes as 14 and plus minus, this will be close to minus 9 farads. So this is the value of the capacitance CA. Now we can easily find out the energy stored, because this capacitor is connected to one 10 volt battery. So we can say that our energy stored let us call that our UA will be equal to half CA V square. Simply substitute the values, we get this is 2 into 10 raised to power minus 9, and the voltage is over 110 whole square. So we get our energy stored in the capacitor, that is our UA will be equal to, this will be our 1.21 into 10 raised to power minus 5 joules. So this is our part A. Now we come to our part B. And in part B states that the battery is disconnected and dielectric slab is removed. And we have to remember that the amount of charge stored on the capacitor is going to remain same with and without the battery. So first of all, let's find out the charge stored in the capacitor. So you can say charge stored in capacitor A, let us call that as a QA, and that will be equal to capacitance of A multiplied by supply voltage V, and from here we get our QA will be equal to CA was our 2 into 10 raised to power minus 9, and voltage is our 110. So this gives us that our QA, that is the charge on capacitor, will be equal to 2.2 into 10 raised to power minus 7 coulombs. And this charge is going to remain constant even after the removal of the battery. Therefore, we can say that this charge remains constant even after battery is disconnected. Battery is disconnected. But now the dielectric is removed, so because of this the capacitance of A capacitor is going to change, or we can say it will be reduced. When slab is removed, capacitance of A will get reduced. and let us call that capacitance as Ca prime, and we can say that our Ca prime will be equal to epsilon naught, and this is our dielectric constant, is our okay, we need to find out the work done. Okay, and this comes as 2 times A and divided by D. So this will be equal to, we have this as 8.85 into 10 raised to power minus 12, and this comes as 0.04 and divided by 8.85 into 10 raised to power minus 4. We get that our Ca prime will be equal to 0.4 into 10 raised to power minus 7 farads. Yeah, so first the capacitance was our 2, now it comes as 0.4. Therefore, the work done will be the difference between the energy. Okay. So energy will be our UA prime so we need to find out the amount of work done. So we can say that the work done to remove the slab that is our W will be equal to UA prime minus UA, and UA prime we can find out our UA prime will be equal to, we have our charge we found out is our Q, that is 2.2, and so this will be coming as close to 6.05 into 10 raised to the minus 5 joules. And now we can just substitute the value. We get this as work done will be equal to 6.05 minus UA, we've already found out, is 1.21 into 10 raised to the power minus 5, which gives us that the work done is equal to 4.84 into 10 raised to the power minus 5 joules. And now we come to our C part. Part C. And in part C it states that the same dielectric slab is now placed inside B, and then they are connected as in figure 3. Okay, so we have to find out the energy stored in the system, that is energy of A and energy of B. So first of all, let's find out what will be the, you can say, capacitance of capacitor B with the dielectric. You can say capacitance of capacitor B with dielectric, let us call that a CB, which will be equal to K epsilon naught A divided by D. K is given to us as 9, and this as 8.85 into 10 to the power minus 12, and area of B is given to us as 0.2. One second. The plate areas of okay. Here we have to keep in mind that the area of the dielectric, especially in, you can say, our in first part, we have to make sure, because the area of the dielectric will be equal to area of the our capacitor B. Okay, because the dielectric fits the capacitor B completely. Okay, so we have to make sure, that's why we have taken the area as 0.02. So we have to keep this in mind, otherwise it will be a little bit tricky. And this comes as 0.02, and it comes as 8.85 into 10 to the power minus 4. Therefore, we get our CB will be equal to 1.8 into 10 to the power minus 9 farad. Okay. And once again, the two capacitors are in our parallel. You can say that our C A and B are in parallel. Therefore, the capacitance of the system, that is our C, will be equal to CA prime plus CB. And we already know these values. CA prime was our 0.4 plus 1.8 into 10 to the power minus 9. This gives that the capacitance of the system will be equal to 2.2 into 10 to the power minus 9 farad. And the charge on the system will be only charged because of the capacitor A. There is no charge on the capacitor B. Okay. So we can say that the charge on the system let us call that as Q, that will be equal to QA, and QA is our 2.2 into 10 to the power minus 7 coulombs. Now we can easily find out the energy stored. Energy stored in the system will be equal to U is equal to half Q square divided by C. This is capital Q square, and we get our U is equal to our half, Q is our 2.2, 10 to the power minus 9 whole square, and the capacitance is also about 2.2 into 10 to the power minus 9. This gives us that our U is equal to 1.1 into 10 to the power minus 5 joules. So the only tricky part here, we have to remember that the area that will be associated, especially for case 1, will be equal to that the area will be equal to of our dielectric, that is our the of plate B. We have to remember this part, and this is specifically for the area part. Next question. It was asked in the year 1994, and it states that two square metal plates of side 1 meter are kept 0.01 meter apart like a parallel plate capacitor in air in such a way that one of their edges is perpendicular to an oil surface in a tank filled with insulating oil. The plates are connected to a battery of EMF 500 volt. The plates are then lowered vertically into the oil at a speed of 0.001 meter per second. Calculate the current drawn from the battery during this process. The dielectric constant of the oil is 11 and value of epsilon naught is given to us. So in this case, we are given that we are having we can just draw an approximate figure for that. Let us suppose this is a container and it is the oils are something like this, and we have a parallel plate capacitor, and that parallel plate capacitor is being lowered into the oil tank, something like this. So these are the plates of the capacitor, so which will be perpendicular to the oil, and the velocity of the lowering is given to us, and let us assume that at any given moment the distance of these plates in the oil is, let us suppose, given as x. So outside will be equal to 1 minus x. And so ideally this entire setup will be consisting of now two capacitors. One capacitor will be of which is in the air, so this is our air, and the other capacitor is because of the oil, because of the dielectric basically. So its capacitance is going to change. We can call it as a different capacitor. So now the single capacitor, once it is being lowered inside the oil, it is going to behave like a two capacitance. Okay, and these two capacitances will be the equivalent capacitance of this will be equal to the capacitance because of the air plus capacitance because of the oil. Okay, basically they will be acting in they are in parallel connection. So first of all, let's find out the individual capacitances. So we say that let length x of plates is immersed in the oil. Therefore, we can say that length of plate in the air, length of plates in air will be equal to 1 minus x. Now we can find out the area of the plates in the oil and area of the plates in the air. We can say that area of plates in oil, let us call that as A oil, and this our A oil will be equal to our 1 multiplied by x. This comes as x, and it is in meters. Yeah, it is in meters, so this comes as x meter square. Similarly, we can find out the area of plates in the air. Area of plates in air, let us call that as A air, and that will be equal to over 1 minus x multiplied by 1, which gives us 1 minus x meter square. And the distance between the plates is going to remain same. So this distance will be same whether the plates are in air or in oil. So based on this, we can easily find out the capacitance of the part immersed in oil and the capacitance which is not in the oil, that is in air. So we can say that capacitance of the part immersed in oil, let us call it as C oil, then this C oil will be equal to dielectric constant, that is K epsilon naught A divided by D, and A is our area of the oil and K is given to us, that is our 11, epsilon naught area we just found is our x, and D is our 0.01. Similarly, we can find out that the capacitance of the part in the air. Capacitance of the part in air, let us call that as a C air, and this C air will be equal to epsilon naught area in the air and divided by D. So we get this as epsilon naught area is our 1 minus x and D is our same, that is 0.01. And the total capacitance, these both C oil and C air both are in parallel. Therefore, we can say that total capacitance that is our C will be equal to C of our oil plus C of the air. So we substitute it, we get our C, and our for oil is our 11 epsilon naught, and this is our x divided by 0.01 plus, and we have epsilon naught, and this is 1 minus x divided by 0.01, and we can take things as common, that is epsilon naught upon 0.01, and we are left with our 11x plus 1 minus of x. So we get our C will be equal to, this will be epsilon naught 0.01, and this comes as 10x plus 1. So this is our capacitance, and based on this, because it is given that this capacitor is connected with a voltage source of battery EMF of 500 volt. Based on this, we can find out the charge, and based on the charge, we can find out the current. So we can say that charge on the capacitor charge on the capacitor, if given as Q, that will be equal to C multiplied by V. C we already know, so we can write our Q will be equal to epsilon naught 0.01 10x plus 1, and the supply EMF is given to us as 500. Now we need to find out the current. Current will be the derivative of the rate of change of the charge. So we can say that our current let us suppose that is given as I will be equal to dq by dt, and this comes as d of dt, and we have here epsilon naught upon 0.01 10x plus 1 multiplied by 500, and we can take the things which are common outside the derivative. So we get our I will be equal to, we get this as 500 epsilon naught 0.01, and that will be di of dt of this 10x plus 1, because x is changing as it is moving, so it can't be constant. So dx by dt, and 1 is our obviously constant. So this comes as 10 multiplied by dx by dt, and this dx by dt is nothing but our velocity that is given to us. So we substitute it, we get this as 500 epsilon naught 0.01, and dx by dt is 0.001, and this comes as 1000, this comes as 10, so we get this as, one thing I missed is 10. So we get that 1000 goes 500. So this our current I will be equal to 500 times epsilon naught. We substitute value of epsilon naught, that is 500 8.85 into 10 raised to power minus 12. This gives us that the value of current is approximately equal to 4.425 into 10 to the power minus 9 amperes. So this is the current drawn from the battery. So this was the only thing, was current drawn. Next question, and it was asked in the year 1995, and it states that 2-point charges plus q and minus q are held fixed at minus d0 and d0 respectively in of a xy coordinate system. Then we have to find out which of these option will be correct. First one is related to the electric field, second one the work done, and the third is also electric field. In the first case it says that with respect to x-axis, and that is on y-axis, and finally is the dipole moment. So we can just draw the basic approximate figure. So we are given that 2 points plus q and minus q. So we have plus q at so we have minus q is given at d comma 0, and we are given plus q at minus d comma 0. Okay. And we are interested in finding out first of all the electric field, then work done, and then also electric field, but with respect to y-axis, then the dipole moment. Okay. So let us start by, first of all, it is much easier to calculate the dipole moment. So let's find out the dipole moment. So we are given that we are having a charge plus q, and that plus q charge is located at a distance of minus d0, and we have a charge of minus q that is at a distance of a coordinate system of d comma 0. And we already know the formula for dipole moment. So we have our dipole moment, that is our P will be equal to Q multiplied by Q dot D, and this is the distance between the charges, and this distance between the charges, this is our D, and this will be equal to our 2D. And we substitute, we get this as Q, and this is about 2D, and along our iota vector. Okay. And so we can say our dipole moment P will be equal to 2qd and our I vector, and it says that it is along our x-axis. Okay. And the dipole moment is, we can say, or we already know that it is from the negative charge to the positive charge, so it has to be through the negative x-axis. Okay, so we have to remember that thing. So we can say the dipole moment is from negative charge to the positive charge, that is along negative x-axis. Negative x-axis. So therefore option number D is incorrect. Next we are going to find out the electric field, and first in case is along x-axis. Okay, so let us electric field along x-axis. Now it is directly based on the principle of superposition. You can say principle of superposition. Principle of superposition. So if we assume that there is a point P on the x-axis, because we have two charges, one is our plus Q and another one is our minus Q, therefore we can say that for a point P on x-axis, the electric field due to first charge is about positive, So we can say due to positive charge, that is positive Q, and is directed away from the charge, away from charge, and because of the minus Q is directed towards the charge, directed towards the charge, or we can just represent it diagrammatically also. So this is a plus Q, and the electric field will be directed away from the charge, and for minus Q it will be directed towards the charge. Okay. So therefore, because the point P is not exactly given to us, that where this point will be, so we can say the net electric field at point P will be depending upon the relative position of point P. Therefore we can say that net electric field will depend on the position of point P. Point P relative to the charges. Relative to charges. So we cannot for sure say that it will be in same direction at all points it is written. Okay, so which is incorrect. Next, we can make analysis of electric field along the y-axis. You can say electric field on y-axis electric field on y-axis. For that we can just draw our approximate figure. So we have a this is first charge, this is given as Q minus D and 0, which is our plus Q, and this is second minus Q, that is D comma 0, and this is our point where we are going to find electric field, which can be along this y-axis at any point. Okay. And so electric field, because of this plus, will be in this direction. Let us call that as our EQ, and because of the negative charge it will be in this direction. Let us call this as E minus Q, and we can divide it into two components. So here we are going to get EQX, and this will be our EQY. Similarly, we are going to get E minus QY, and this will be our EQ minus QX. E minus QX. So therefore, from the figure itself, we can say that this will be our net electric field. Let us suppose given as capital E. So from the figure we can say that our net electric field electric field is along positive x axis, and so option number C is the correct one. Option C is correct. Now we have to find out the work done. In work done, it states that test charge from infinity to origin. Okay, and let us suppose that test charge is given as Q naught. So we can say work done in bringing test charge Q naught from infinity to origin. So we can just write the formula for work done. So work done will be equal to test charge Q and the difference between their potential. And origin potential is a V naught and infinity is the infinite potential. Okay. And we know that potential at any point potential at any point, that is our V, it is given as K Q upon R, where R is the distance between the point. Okay, and this is our origin O, and this origin is equidistant from both the charges, and the charges are of opposite. Okay, so therefore both charges are going to contribute equal potential at point O, but because of the opposite polarity, the net potential will be at at origin will be equal to 0. So you can say that at origin the contribution from both charges we can say net contribution from both the charges will be equal to 0. Therefore we can say our V naught will be equal to 0, and obviously at infinity the potential will be automatically 0 because R is our on the infinity part. So this gives us, we can say also V infinity is equal to 0. Therefore we can say our work done will be equal to test charge is our Q 0 minus 0 giving us 0, and here work done is said to be work has to be done. It says the work has to be done, so this option is also incorrect. No work is to be done. So the only option correct is our option number C is the correct one. Next question. And it states that it was asked in the 1995, and it states that a parallel plate capacitor of capacitance C is connected to a battery and is charged to a potential difference V. Another capacitor of capacitance 2C is similarly charged to the potential difference 2V. The charging battery is now disconnected and the capacitors are connected in parallel with each other such that the positive terminal of one is connected to the negative terminal of the other. The final energy of the configuration is. So here we are given that we have two capacitors. Okay, so let us draw the approximate figure. So this is first capacitor having capacitance of C and it is charged to a potential difference of V. So supply voltage we can assume that it is V and the charge on the potential difference on the capacitor C is equal to V. In the second case, we are given that we have a capacitor which is our 2C and it is charged to a potential difference of 2V. So it is having a potential difference of 2V. And in the, you can say, final configuration, both the capacitors are connected in parallel. Okay, so we can also draw it. Let us call this as C1 and this is our C2. So first capacitance and second capacitance, and it says that in such a way that positive of one is connected to the negative terminal of the other. So this is our positive, negative. So this will be negative and this will be our positive. Okay, in this way they are connected. And we can find out the charge on first capacitor and the charge on the second capacitor. We can say charge on C1, let us suppose that is given as Q1 and that Q1 will be equal to C multiplied by V, and we can write that our charge on C2, let us Q2 will be equal to twice C multiplied by twice V, which gives us 4 times CV. And it says that both the capacitors are connected in parallel. And so if they are connected in parallel, obviously they should be having a common potential, which we can find out, you can say, by using the formula. And we can say that since capacitors this is, let us suppose, C1 and this is our C2, C1 and C2 are in parallel, therefore the common potential let us call that as V prime, then this V prime will be equal to Q2 minus Q1 divided by C1 plus C2, and we get from here our V prime will be equal to 4 CV minus CV divided by C plus 2C, which gives us, this will be coming as 3 by 3 and this comes as CV by C. 3 and 3, C and C goes away and this comes equal to V. And they are in parallel, so we can find out a net capacitance. So we can say the equivalent capacitance C prime will be equal to C1 plus C2. That is C plus 2C is equal to 3C. Now we can find out the energy of the system. Energy of system will be equal to half C prime V prime square. So this comes as half, this is our 3C, and V prime is our V whole square. Therefore we get energy of the system will be equal to 3 by 2, and this comes as CV square. And we can also, if we are not aware of this particular formula, anyway this we should be knowing, but if still we don't know, then we can use the concept that the net charge, because they are having a different charge, so this charge will be shared between the two capacitors, and we can just use that approach also. So let me solve that also. So this is our second method. In second method, we can find out the net charge shared between the two capacitors. Net charge shared by two capacitors. Let us call that as our Q prime, which will be equal to Q2 minus Q1. So this is our 4CV minus CV, which gives us that our Q prime will be equal to 3CV. And the capacitor should be having a common potential, that is V prime. But before that, let us find out the net capacitance, because they are connected in parallel. So you can say equivalent capacitance, that is a C prime, which will be same which we just calculated, that is C1 plus C2, and that will be equal to 3 times C. And now we can find out the potential difference across the capacitors, because they will be the same, you can say same potential. So you can say the capacitors will have same potential and let us call that as V prime. So V prime will be equal to our Q prime upon C prime, and that comes as 3CV and divided by 3C, which is our V. So ultimately we are going to get the same answer. Now we can find out our energy. So we can say our energy will be equal, let us suppose our U prime is equal to half C prime V prime square, and this will be coming as 3 by 2 CV square. So it comes as 3 by 2 CV square. Option B is the correct one. Option B is correct. Next question. was asked in the year, you can say 1996, and it states that the capacitance of a parallel plate capacitor with a plate area A and separation D is C. The space between the plates is filled with two wedges of dielectric constant K1 and K2 respectively, as in the figure. Find the capacitance of a resulting capacitor. So we are given this basic figure. So this is the plate of the capacitor, and inside it we are having two different dielectric. One is having dielectric constant K2 and another one is having of K1. Okay. And we have to find out the resulting capacitance because of this insertion. Okay. And we already know that so in this case we are going to consider a so here let's start from the basic definition of the capacitance, that is dependent upon and we say that let the length of the capacitor, length of capacitor is given as L, and breadth of capacitor, let us suppose, is given as B, and D is the distance between the plates of capacitor. Distance between plates is, let us suppose, given as D, and so we can consider that we can just draw a 2D figure for it. It will be much more convenient to explain that way. Okay. So we have the breadth of the capacitor, this is a B, and distance between the plates, that is given to us at D, and it is divided into two parts like this. So here we are having our K1 and this is our K2, and let us consider a small area, something like this. Its width is dx, and here this angle is, let's suppose, theta, and the width here is our y, and this is our d, so this comes as d minus x, sorry, d minus y. So this small portion dx which we have considered, it is, you can see, into two parts. One part is associated with dielectric constant K1 for y and dielectric order K2 with respect to d minus y. And suppose this angle is our theta and we call this as our x. Therefore, we can say that a small capacitance that is associated with K1, let us call that as a DC1. We can say that our capacitance DC1 associated with dielectric constant K1 associated with dielectric constant K1, then we can say that our DC1 will be equal to, we have the dielectric K1 and we have our epsilon naught, and its area will be equal to our B times dx, and we get this as d, tangent of theta, this comes as y, and this can be written as d minus x tangent of theta. And the tangent of theta can be written as, so we can just sort it out. So we can write this as our K1 and we have epsilon naught B times dx, this is d minus x, and our tangent of theta will be equal to d upon L. So we can just formulate it, and this will be equal to our K1 epsilon naught, and we have this as B dx, and d can be taken as common excuse me, and we can write this as d L minus x, and this will be equal to our multiplied by L. So we get that our B into L will be giving us area. Yeah, so we can say that our DC1 will be equal to K1, and this is our epsilon naught B into L will be giving us a area times dx, and this comes as d L minus x. So this is our DC1. Similarly, we can find out our DC2. Similarly, our DC2 is our K2 epsilon naught, this comes as B dx, and we get this is tangent of theta, and we substitute it d by L tangent of theta, so this comes as K2 epsilon naught B dx, and this is our x upon, one second, x tangent of theta. And we substitute value of theta, tangent of theta, so we get this is x multiplied by d, and here goes our L. So once again B into L will be our area. So we get this as DC2 will be equal to our K2 epsilon naught A dx and divided by our x multiplied by d. So we got our DC2. And for area we can just draw an approximate figure. So this is our area and length is our L and this is our B. So our area will be equal to B times L. And these two capacitors are in our series. These two means DC1 and DC2. So we can say that our DC1 and DC2 are in series. Therefore, 1 upon DC is equal to 1 upon DC1 plus 1 upon DC2. And we simply substitute the values. We get this as K1 epsilon naught A dx, and this comes as dl minus x, plus this is our K2 epsilon naught A dx, and this comes as x times d. So now we just solve it, and we can take here something's common, and that will be equal to, this comes as d upon epsilon naught A dx, and we are left with L minus x upon K1 plus x upon K2. K1 K2 will be our K1 multiplied by K2 will be our LCM. So we get this as d epsilon naught A and times dx. We get here K1 times K2, and that will be equal to K2 L minus x plus K1 times x. So now we can find out our DC. So we get our DC will be equal to, this comes as epsilon naught and A K1 K2 and divided by D, this is our K1 L minus x plus, sorry, not K1 but K2 L minus x and K1 x, and this is our derivative d of x. And we can just make some adjustment here. So we get our DC will be equal to epsilon naught A K1 K2 D. We multiply K1 K2 inside, so we get this as K2 times L, and this will plus x we can take as common, so we get this as K1 minus K2, and we get this as d of x. Now this, like here we have considered d of x, similarly we can consider other portion d of x like this, and similarly like this. So it will be a continuous process. So we are going to start from 0 and the x is going to vary from the entire distance, that is our length L. So we can say that this DC, that is infinitesimal capacitor, DC will add as a parallel plate capacitor, as the capacitors connected in parallel, as capacitors therefore as capacitors from x equal to 0 to x is equal to capital L. So we can just draw approximately here also. So this is our x equal to 0 and this is our x equal to L, and we can consider this small, these are our first DC, and similarly we can draw a second DC small portion, and similarly the third one, and this will be continuously added up till here, the last one. So this is our DC, 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 so it will be added across from x equal to 0 up till x equal to L. Therefore we can say that our net capacitance, that is our C, will be equal to integration from x to 0 to L, and this is our DC. Now we can just substitute it. So we get 0 to L, and DC we found it our epsilon A, K1, K2, this comes as D, K2 L plus K1 minus K2 times X, and rest of the things are constant except this portion. Okay. And this will be coming as the you can say log, natural log rather. So you can say our C will be equal to, we have our epsilon A, K1, K2, this comes as K1 minus K2 times D, and we have a natural log of K2 upon K1. So this is our net capacitance of the given question. Next question rather, it was asked in the year 1996, and it states that the magnitude of the electric field E in the annular region of a charged cylindrical capacitor. So we have to find out the annular region and electric field in annular region. For that we can just draw an approximate figure, and okay, we have cylindrical capacitor. Let us draw the axis. So this is our axis, and this is our internal cylinder, and this is our external one, and we can consider a Gaussian surface which is inclusive of both. So this is our Gaussian surface, and the length of this Gaussian surface is L, and the radius of this Gaussian surface is our R. So this is our Gaussian surface. So we have here two cylinders. We assume that the inner cylinder radius is suppose A and the outer cylinder radius is suppose B. Okay. And we are only interested in the region where the radius is greater than A but less than B. So we are only interested in this region, radius greater than A but less than B. We can say that inner cylinder radius let us suppose given as A, and outer cylinder radius that is of B, and let us suppose that L is the length of the Gaussian surface, and we are interested in the annular region. So we can say a annular region, that is our A, R is greater than A but less than B, and we have to find out the electric field between this. So we consider a Gaussian surface. Consider a Gaussian surface of length L and radius R, and a radius R. Therefore, we can write that for a closed surface, electric field and its area will be equal to the charge enclosed divided by epsilon naught. Okay. And if you consider a linear charge density lambda, so you can say for charge density lambda, this Q enclosed will be equal to lambda multiplied by length, that is a Gaussian surface. And we can write that our electric field multiplied by 2 pi RL will be equal to lambda L divided by epsilon naught. So from here we can say our electric field is equal to this length and length goes away. Electric field comes as lambda upon 2 pi R and epsilon naught. Therefore, from this equation we can write that our electric field is inversely proportional to R. So we can say that the electric field varies. Option C is the correct one. Option C is correct. Next question. Okay, so this is more or less a conceptual one. We are given that a metallic solid sphere is placed in a uniform electric field. The lines of force follow the path as shown in the figure. So we have these 4 lines of forces which we are we are going to find out which of them will be the correct one. Okay, and it is given that this metallic solid sphere is placed in a uniform electric field, and we know that these are a representation of nothing but electric lines of forces, and this is our metallic, so we can say this is our conductor. And if this is conductor, so we can say our electric lines of force, so we can say our electric lines of force cannot enter the metallic sphere. Therefore, the electric field inside the this metallic solid sphere is equal to 0. Therefore, we can say that electric field inside the metallic solid sphere is equal to 0. And we can also draw the same conclusion by the positioning of the movement of the electrons. Okay. And all the electric lines, all the field lines, or we can say force, is from left to right in this direction, and the movement of electrons will be in the against the direction of electric field. So we can just draw approximate figure. So this is our conductor. Electric field is from our left to right, but the movement of electrons will be from right to left. So because of this, the left side will be rich in electron, basically having negative charge, and the right face will be deficient, giving us a positive one. Okay. And so we know that for a negative, the field are terminating point, so this will be our terminating point, and for positive it is a originating point, so it will be the originating one. So inside it will be equal to 0. So same conclusion. Okay. So we can say that the electric field is from left to right. Electric field is from left to right. So you can say electrons move from right to left. Right to left. Therefore, you can say left face is having a negative charge, and our right face is having a positive charge. And we know that field lines terminate on negative charge. Field lines terminate on negative charge, and originate from the positive charge. Originate from positive charge. So we can say that end point will be left face and start point will be right face. We can say the end will be our left face and start will be the right face. Therefore, option 4, that is option number D, is the correct one. Option D is correct. So these were the questions which were asked in the year 93, 94, 95 and 96. Total of 8 questions. So this completes all 8 questions. Thank you.